There is something sitting at the center of nearly every galaxy in the observable universe, something so extreme, so violent, so fundamentally strange, that even the greatest scientific minds who ever lived struggled to accept that it could actually be real. And here is the part that should make you stop whatever you are doing right now. We now believe that these objects, these black holes, are not just curiosities floating out in space. They are windows. They are, in fact, the most powerful diagnostic tools nature has ever handed us. And they are forcing us, slowly, uncomfortably, magnificently, to rethink everything we thought we knew about space, time, and the very fabric of reality itself. If you have ever looked up at a clear night sky and felt that strange cocktail of wonder and insignificance, this video is going to hit differently. Because by the time we reach the end of this conversation, you are going to understand something that most people, even highly educated people, have never really sat with. You are going to understand why physicists believe that space and time might not be fundamental things at all. That they might be illusions built on top of something far stranger and far deeper. And black holes are the reason we even started asking that question in the first place. So let us go back to the beginning. Not the beginning of the universe, we will get there, but the beginning of the idea. Because the concept of a black hole is older than you probably think. And it did not come from Einstein. Even though Einstein would eventually give us the mathematics to truly understand them, it was the 1780s, England and France. Two men working independently on opposite sides of the English Channel arrived at almost exactly the same thought. One was a quiet English clergyman and amateur scientist named Jean Michel. The other was Pierre Simon Laplace, one of the greatest mathematicians France ever produced. And the idea they were both turning over in their minds had to do with something called escape velocity. Escape velocity is the concept that if you want to throw a ball from the surface of a planet and have it escape into space and never come back, you need to throw it fast enough. For Earth, that speed is about 7 miles per second, roughly 20,000 miles per hour. That is fast. But it is a number. It is a speed you can calculate. And here is the key insight. That number depends on how massive and how compact the object is. A bigger, denser planet has a higher escape velocity. Makes sense. If you go to Jupiter, the escape velocity is much higher. If you imagine an incredibly dense, incredibly massive star, the escape velocity at the surface starts climbing dramatically. And then both Michel and Laplace asked the same quiet, almost casual question. What if you could make a star so massive, so dense, that the escape velocity at its surface exceeded the speed of light? In that case, light itself could not escape. You would not be able to see it. The star would be effectively invisible. A dark star, a black star, what we would eventually call a black hole. It was a beautiful thought, elegant, almost poetic, but it was also, at the time, untestable. And so the idea drifted into the background, filed away under the category of interesting speculation. It would take over 100 years before it came roaring back, this time carried by one of the most radical and far-reaching theories in the history of human knowledge. In 1915, Albert Einstein published his general theory of relativity, and within that theory was an entirely new picture of what gravity actually is. Gravity, Einstein told us, is not a force reaching across space the way Isaac Newton had described it. Gravity is geometry. Massive objects bend and curve the fabric of space-time itself, and other objects then follow those curves. The Earth does not pull the moon toward it. The Earth curves space-time, and the moon is simply following the straightest possible path through that curved geometry. The mathematics of this theory was stunning. Within months of Einstein publishing his equations, a German physicist named Karl Schwarzschild, who was at the time serving on the Russian front in World War I, solved those equations exactly. He was doing physics in the trenches, and what he found was extraordinary. There was a solution to Einstein's equations that described something remarkable. A point of infinite density, surrounded by a boundary in space-time beyond which nothing, not even light, could return. He sent his solution to Einstein in a letter. Einstein was impressed. He was also somewhat uncomfortable, because the mathematics were pointing at something he was not sure could actually exist in nature. That discomfort would linger for decades. Einstein himself, as late as 1939, wrote a paper arguing that black holes could not actually form. He believed the mathematics were telling us something about the limited theory, not about a real physical object. He was wrong. And the story of how the physics community eventually accepted that black holes are real is itself a fascinating and deeply human story, one involving long arguments. Dismissed papers and eventual triumph, the term black hole itself was not coined until 1967, when the American physicist John Wheeler used it in a lecture and it immediately stuck. because it perfectly captured the essence of the thing, a hole in the fabric of space, a point of no return, a trapdoor in the universe. But here is where the story starts getting truly strange. And this is where most science writing leaves you behind, because it stays on the surface of what black holes are and never gets to what they mean. So let us go deeper. Once physicists accepted that black holes were real, they started asking, well, what exactly happens at the boundary? That boundary has a name, the event horizon. And the event horizon is one of the most conceptually bizarre things in all of physics. From the outside, watching something fall into a black hole, you would never actually see it cross the horizon. Because of how gravity warps time itself, a prediction straight out of Einstein's general relativity, you would see the infalling object slow down, getting dimmer and redder as the light from it stretches until it seems to freeze at the boundary and fade away. From your perspective outside, the object never crosses. Time, as measured by that infalling object, appears to stop. But from the perspective of the object itself, it crosses the event horizon smoothly without even noticing. No warning sign, no physical jolt, just space-time so warped that every possible direction of travel, every future path through space-time, points inward. There is no way out, not because of some force pushing you back, but because inward is the only direction the future can go. The interior of a black hole is not really a place in space at all. It is a moment in time. And the singularity at the center, that point of infinite density where the mathematics breaks down completely, is not a location you fall toward. It is the end of time itself. Let that sink in for a moment. The singularity is not a place. It is a moment. It is a boundary beyond which time simply stops having meaning. And what happens there, what the laws of physics say about that point, is something our current theories cannot tell us. The equations produce infinities, and infinities in physics are a confession of ignorance. They're the theory's way of saying, I have reached the edge of my validity. You need a better theory. And this is where black holes begin their second life as one of the most important research objects in modern physics. Because that breakdown at the singularity is not just an inconvenience, it is a clue. It is a pointer towards something deeper. And the pursuit of that deeper understanding has become one of the central dramas of 21st century physics. To understand why, you need to know a little about the two great pillars of modern science, the two theories that together describe essentially everything we can observe in the universe. The first is Einstein's general theory of relativity, which describes gravity and the large-scale structure of space-time, planets, stars, galaxies, the expanding universe. The second is quantum mechanics, which describes the behavior of matter and energy at the smallest scales, atoms, electrons, photons, and the fundamental particles and forces that make up everything. Both of these theories are spectacularly successful. General relativity predicts the existence of gravitational waves, ripples in space-time itself, which were directly detected for the first time in 2015. Quantum mechanics underlies every semiconductor, every laser, every piece of modern technology we have. They are the two most precisely tested theories in the history of science, and they are fundamentally incompatible. When you try to apply quantum mechanics to gravity, when you try to write down a quantum theory of gravity, the mathematics collapses, you get infinities everywhere. Meaningless answers. The theories put together start screaming at you. They cannot both be right in their current form. One of them, or both of them, must be an approximation to something deeper, something that reduces to general relativity in some regimes and to quantum mechanics in others, but that at its core is a single unified description of nature. The quest for this unified theory, what physicists call a quantum theory of gravity, is arguably the greatest unsolved problem in all of science. It has been unsolved for almost a century, and black holes are central to solving it, because at a black hole, specifically at the singularity and at the event horizon, both gravity and quantum effects become important at the same time. A black hole is a laboratory for the collision of these two theories. Now we reach the moment when the story takes one of the most dramatic turns in the history of physics. The moment when Stephen Hawking changed everything. In the early 1970s, Hawking was thinking about black holes and quantum mechanics. At the time, the prevailing view was that black holes were perfectly cold, perfectly dark, perfectly inert. Once something fell in, it was gone forever. The black hole simply sat there, unchanging. For as long as the universe existed, Hawking discovered that this was wrong, profoundly, shockingly wrong, and his argument was one of those rare pieces of physics that, once you understand it, feels both surprising and somehow inevitable. Here is the key insight. Quantum mechanics tells us that empty space is not actually empty. At the quantum level, the vacuum is constantly seething with activity, pairs of particles flickering in and out of existence, appearing from nothing and then annihilating each other almost instantly before their existence would violate the laws of conservation of energy. These are called virtual particles. They are a fundamental feature of quantum field theory. Not a quirk or a metaphor, but an actual, measurable prediction that has been confirmed in experiments. Now imagine this process happening right at the edge of a black hole's event horizon. A pair of particles appears. One falls just inside the horizon, the other just outside. And rather than immediately annihilating with its partner, which is now behind the horizon and unreachable, it escapes. It flies off into space. From the perspective of a distant observer, this looks like the black hole has emitted a particle. It looks like the black hole is radiating. This is Hawking radiation. And it has a temperature. A black hole glows, not with visible light. In most cases, the temperature is fantastically cold for large black holes, but it genuinely emits thermal radiation, exactly like a hot object emitting infrared light. The more massive the black hole, the colder the temperature. The smaller the black hole, the hotter and the faster it radiates. This was published in 1974. The physics community was at first skeptical, then stunned, then convinced, because Hawking's calculation, however you approached it, kept giving the same answer. Black holes radiate. They are not eternal. They evaporate. A stellar mass black hole, the kind formed when a large star collapses at the end of its life, would take incomprehensibly longer than the current age of the universe to evaporate through Hawking radiation. But eventually, given enough time, every black hole evaporates. It shrinks, slowly radiating away its mass energy as a faint glow of thermal radiation until finally, in the far, far future, it is gone. The black hole disappears, and all that is left is that radiation spreading out through an otherwise empty universe. And this is where the real crisis begins. The crisis that, for more than 40 years, has been the most important unsolved puzzle at the intersection of quantum mechanics and gravity. It is called the black hole information paradox, and it is, in its own way, a paradox about the deepest nature of reality itself. Here is the problem. Quantum mechanics has a rule, a deep foundational rule that is baked into the mathematical structure of the theory. Information cannot be destroyed. The technical statement is that quantum evolution is unitary, which is a way of saying that if you know the exact quantum state of a system at one moment in time, you can in principle reconstruct the exact quantum state at any other moment, past or future. Physics is reversible in principle. Information is conserved. This is not just an abstract principle. It is connected to some of the most fundamental features of quantum mechanics. If information could truly be destroyed, the whole mathematical framework would collapse. Probabilities would stop adding up to 1. Causality itself would be undermined. Physicists take the conservation of information very seriously. Now consider what happens when a black hole evaporates. You throw a book into a black hole. The book contains information, the words on its pages, the positions of every atom, the quantum state of every particle. That information falls past the event horizon. The black hole then slowly evaporates, emitting Hawking radiation. But here is the thing that Hawking's original calculation showed. The radiation that comes out is purely thermal. It is random. It carries no information about what fell in. The book is gone. The information is gone. Destroyed. Erased from the universe forever. But that violates quantum mechanics. You cannot destroy information. It is one of the non-negotiable features of the theory. So you have general relativity and quantum mechanics producing a flat-out contradiction, a paradox that cuts to the heart of both theories. This became known as the black hole information paradox. And it is not a technicality. It is not a minor inconsistency that physicists quietly work around while everyone else is not looking. It is a crisis, a genuine, profound crisis that has occupied some of the best minds in theoretical physics for decades. Hawking himself, for most of his career, took the radical position that information really is destroyed in black holes, that quantum mechanics needed to be modified at its foundations, that something genuinely new and revolutionary was required to resolve the paradox. Most other physicists found this position deeply uncomfortable because modifying quantum mechanics at its foundation tends to break physics in very ugly ways. The debate raged for years. There were famous bets. There were international conferences, there were papers and counterpapers, and slowly, painfully, through a series of insights that built on each other over 2 decades, a new picture began to emerge. The key piece came from a remarkable theoretical discovery in 1997 made by Joan Maldacena, an Argentine physicist working at Harvard at the time. Maldacena discovered something that sounds almost mystical, but is mathematically one of the most solid results in modern theoretical physics. He showed that a theory of gravity in a particular kind of space is exactly equivalent, mathematically perfectly, precisely equivalent to a quantum theory without gravity defined on the boundary of that space. A 5-dimensional theory of gravity is equivalent to a 4-dimensional quantum theory on the boundary. The two theories describe the same physics, just from different perspectives. This is called the AD-SCFT correspondence, or sometimes holographic duality, and it had explosive implications for the information paradox, because quantum theories, the boundary theory in this correspondence, definitely obey unitarity. They definitely conserve information. So if the gravity theory and the boundary quantum theory are truly equivalent, the gravity theory must also conserve information. Black holes must not destroy information.